Okay, guys, so we are gonna finish this exercise we started in this example. So remember last class we were doing conservative vector fields, right? So remember we said that a vector field is conservative if there is a function such that the gradient of that function is that capital F, right? That is the vector field. And that function is called the potential function, okay? So we're gonna do this example, this one. So if you get this, so if you get that vector field, okay? So it's saying that this vector is conservative. So find the potential function for it. So we need to find the f, the small f, such that the gradient of f equals f of xy, okay? So where f goes from like R2 to R, okay? So that's why, because it looks like that, the gradient looks like this. So the gradient is derivative of f with respect to x evaluated at xy, comma, derivative of f with respect to y, evaluated at xy, okay? That's how it looks. So let's do it. So let me do it here in OneNote. So the potential the function is example. The function is f of xy equals 3 plus 2xy, right? Plus s squared minus sine of y j. Okay. 3 plus 2xy plus x minus sine x squared sine y. Okay. Okay, so we need to find f that this equals to the gradient of f, and that means that f of this equals f of xi plus f of yj. So what we have is that derivative of f with respect to x I plus derivative of f with respect to y j equals 3x plus, no, 3 plus 2xy I plus x squared minus sine y j. So you see, you from here you deduce this guy has to be equals to this guy, and this guy has to be equals to this guy. Okay. So from here we got derivative of f with respect to x. This is xy, no? 3 plus 2xy. And from here we have derivative of f with respect to y. The xy is s squared minus sine y, right? So from here, so either way we can build the function. So we're gonna start with this function. So what we're gonna do is integrate both sides with respect to x. okay? If you integrate both sides with respect to x, by the fundamental theorem of calculus, you will obtain f. So you will obtain here you integrate both sides with respect to x by fundamental theorem of calculus. This basically, these guys will cancel. So you'll get f of xy equals, because this basically, this is, remember that this is the antiderivative. Integral is the antiderivative of the derivative, right? And this, now we have to integrate with respect to x. Then, so that will be 3x plus 2x squared divided by 2y plus, we're finding the derivative with respect to x, okay? So that will be plus a constant, but the constant depends of y. Okay, that's important detail here, okay? This is what is important, okay? Okay, that cy is the whole trick, okay? Because you're integrating with respect to x, so the constant is not a constant, the constant depends on y. So that's your candidate for your function. However, that's not enough because you need to deduce the cy. But we said that derivative of f with respect to y equals s squared minus sine of y, right? So if I find the derivative with respect to y of this guy, the two things must be the same. So that way I can find c of y. So that's what I'm gonna do. So I'm gonna find the derivative of f with respect to y of this one over here. So that will be the derivative with respect to y of 3x is 0. And these two with these two cancel. The derivative with respect to y of this will be x squared, and the derivative with respect to y of this gives me plus c prime y, right? But on the other side, this guy is x squared minus sine of y. So when you do that, so this square cancel with this one, and you get minus sine of y equals c prime of y. And now, if you integrate both sides, you get the antiderivative of sine is, or minus sine is cosine of y, and this is cy plus a constant. Oh, well, actually cy and then the constant here, d. You can say it like that. So that's your c of y. Okay, so notice that, I integrate here, so I could write constant d1, I could write this constant d2, but at the end, if I do move this constant d1 minus d2, well, that's another constant, so I don't need two constants, right? So I just keep the same constant because this, I don't know what that constant is. Same argument here. You could think, oh, but I'm gonna put plus a constant here, c1y, and this is c2y, but when I make the difference of the two constants, same thing, I have a new constant. So no need to do that. So that's my cy. So finally, this is my solution. So my solution is f of xy x squared y, and cy we said is cosine of y plus d. And we are done. This is my function such that the gradient of this function is gonna give me the vector field that I need. And you can check it. You wanna check it? Let's check it. I know. I'm tired, but I'm not lazy. Let's do it. So derivative of f with respect to x equals 3 plus 2xy. And the derivative of f with respect to y is x squared minus sin of y. As we wanted, okay? Because this is exactly the vector field. 3 plus 2xy, x squared minus sin y. Yeah, correct. Okay, so we move to the next part of the, oops. No, no, it's touching. Okay, oh, I have to do this. Okay, so then we solve this. So then we have the theorem, fundamental theorem of line integrals. Okay, this is important. Because at the end, why is this is gonna be important? Because let's say you have A and B, and you wanna find the path integral between A and B, or the line integral, sorry. So maybe it could be that way, or could be this way. So this theorem is gonna tell you that it doesn't matter which path you choose, the line integral is the same. This is amazing, okay? This is fundamental in physics. This is fundamental in physics. There is, in quantum mechanics, there is something you call path integrals, Feynman path integrals. Feynman is a Nobel Prize of Physics, maybe in the 60s, 1960s. And kind of a similar idea here, okay? Of course, what he does elaborates in a more complicated setting, but this is very important. Okay, so suppose f of xy is a conservative vector field and we wish to integrate along some curve. You want to integrate it along the curve. So as before, you have a vector field. So vector field is this: arrows, 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 arrows. Thinking a magnetic field. And then you have a curve. So let's say this is the curve, yeah. That's your curve. And then, so this is C. Okay. So let's see what happened. So if this is a conservative vector field, I change F by gradient of F, right? So I haven't done anything new. This is a conservative vector field, I change that by that. But by definition of this integral, this is what it means, right? That's definition. And then, so what, by definition, this gradient is this, and this RT is XTI YTJ. So R prime of T is the derivative of this one plus the derivative of this one. Or no, plus IJ, no, but we change the notation. So we are using this notation instead. Okay. So when you multiply this, you get this plus this, the inner product. When you use your inner product, okay, and then here's what people say, then the miracle happens. So what is the miracle? So pay attention, look at this, and try to think why this is true. Okay, so stop it for a minute. The answer is here. But the answer is chain rule. The chain rule we learned a few days ago. Okay, so now you have the derivative and the integral. So they cancel each other because the opposite of integrating is finding derivative. The opposite of adding is subtracting and so on. So these guys cancel each other. So you got this one between A and B. But well, this is the fundamental theorem of calculus, okay? More like, not just, it's more than just canceling because you need to evaluate. If I do have A and B, that they will be canceling. But this is between A and B, so I need to evaluate between A and B. So when I evaluate B, I get this one minus this one at A. And there you go. So you have found the integral between xa ya to xbyb. And it doesn't matter what path you choose, it's gonna be the same integral. So this is called the fundamental theorem of line calculus integrals for conservative vector fields. If f is a conservative vector field with potential function f and it is oriented curve from point A to point B, then we got this. Okay, so this is another formula. And all those things are gonna be useful later. Okay. Okay, so we move to the next section. 6.4. Oh, let me see. Something is wrong with this. I think I have more pages. Oh yeah, this file is broken. Okay, I have to go to the Word file. Okay, so there is more. This is not the end of it. So there's another example. I'll let you check it on the notes. They are on the notes, so you can practice. And then we're gonna do this. Use the fundamental theorem of line of integrals to evaluate this integral, where C is any curve from 0, 0 to 1 pi halves. So let me give you 1 minute to try to do that. And that will be our last example of this section, and then we can start with a new section. I want to try the Green's theorem. Okay. Let me give you 1 minute to do that. Okay, let's do it. So let me check. We have. Let me check. We have. We are recording. Yeah. Okay. So. Use the fundamental theorem of line integrals to evaluate this, where C is any curve from 0, 0 to 1 pi halves. So they're telling us that, so they're saying this is f of xy is this one, e to the x sine of y, e to the x cosine of y. Okay. And then we need to find f such the gradient of f is that. So what does it mean? That we need to fx, fy is that, okay? Or if you want, fx comma fy is that. So we need to find just, it's kind of similar problem to the one we just did. So we need to find f of x, f, and then we just apply the fundamental theorem for line integrals between these 2 points. So let's find f. So we find f. Do I need to do all that? Maybe I want to save some time. Let me see. Between 0, 0. Oh, I need there. Do I have a curve here? Looking at this. Looking to see if I can save some time. Well, anyway. So let's do it. So f of x, the derivative of f with respect to x, xy equals e to the x sine y. So we need to find f of x. So we need to integrate with respect to x. If you integrate with respect to x, then the derivative of e to the x is e to the x sine y plus a constant depending of y. Okay. Now you need to find, we just did, I'm gonna do it fast because we already did this. The derivative of f with respect to y must be equals to the other guy, that is e to the x cosine of y, right? So when I find this derivative, e to the x stays there, and a to the x is cosine of y, okay? Plus c prime of y, okay? So when I compare these two, e to the x cosine y, e to the x cosine y cancel each other. So what I got is 0 equals c prime of y, okay? What does it mean 0 equals c prime of y? That means c prime of y is a constant. Could be any constant. So as we said before, there are many potentials. When you find the potential function that has a gradient f equals to the vector field, any that f plus any constant will do. So you need to keep, you can find thousands of those, okay? So we just need one, so we just can make the constant equal 0. So let's choose c equals 0 just to make our life easier. So when we do that, we got this is 0. So f of xy equals e to the x sine y, right? And now I can apply my line integral. Let me write it down over here. My line integral, fundamental theorem of line integral. The fundamental theorem of line integral says the integral of f dr over the curve equals the integral of the gradient of f inner product dr. So this is inner product, right? Inner product over the curve equals f of b minus f of a, where r of t equals xti plus ytj, and t is between A and B. Okay, so this is XA, YA, that is XB, YB. Okay, so what we need to do is find the integral between 0, 0 and 1 pi halves. So following this, the integral of the vector field that we're doing is oh, let me write it like this. So that's just to help you to follow all these different notations. E to the x sine of x dx plus e to the x cosine of y dy over the curve. This is pxy, and this is qxy. This is the same like this one over here. Integral of f drc. But the one we're gonna do is this one. This is equals to the integral of over the curve of the gradient of f dr. And then all that I need to do is evaluate f at the point 1 pi halves minus f of 0, 0. Don't you love it? This is super nice. Because it's saying from 0, 0 to 1 pi halves. So I just need to evaluate f at that by fundamental theorem of linear integrals. So then, so I evaluate and I get e to the 1 sine pi halves minus f of 0, 0 is e to the 0 times sine of 0, 0. So this is just e to the 1. So we had solved that function, that integral. And remember that that integral represents work. Okay, we did it before. So we talk about it. No, it's in another one. It's not here, but anyway. Okay, so to complete this, to finish, final comments. Suppose F is a conservative vector field and C is a curve from, so this is what we have learned, right? This is fundamental theorem of calculus for linear integrals. Then to observe the value of the line integral does not depend on the actual path. So you could choose this path from A to B, or you could choose this path, okay? And it's gonna be the same answer because you are just counting this one minus this one, okay? So that's kind of amazing. Also, the line integral can still be computed using our earlier method of substituting the parameterization of the curve. So there is the other way to do it, the long way that we did it in exam number 2. But you can do it this way to save time. When a curve begins and ends at the same point, we say the curve is closed. So you get the integral equals 0. So you go here and you finish here. So you go all the way and you finish at the same place. This integral is 0. And then the symbol is often used to mean the curve is closed. So this means the curve is closed. So now you have, I think you had seen those nice notation on Maxwell equation, okay? So another new notation, this means the curve is closed, like the circle, okay? This curve is not closed because it doesn't start where it ends. Okay, so let's see. So let me open now. Well, let me stop here. Let me make a pause here and I'll be back. We're gonna do the green theorem. Okay, guys, so now we're gonna do the Green's theorem. What is it? What happened? No, where did it go? Green's theorem. Okay. So hold on. Can I draw it or not? Okay. So this is the Green's theorem. So what does it say, the Green's theorem? So suppose C is the boundary. Okay, C is the boundary of a rectangle. So the boundary over the rectangle. Okay. So the rectangle is AB cross CD. So the rectangle is the whole thing, no? But the curve is only what is on the around the rectangle. So AB cross CD is the whole thing. This is R, the whole thing, and C is the boundary. Okay. So the integral over C through a vector field P F of x y P of x Q x y. So you know, again, this is there is a vector field. So these are, could be, let's say these are arrows, you know. So, but this means the curve is closed. So if the curve is closed, again, we come back to the same integral we have been solving in the last two classes. But now this is the notation. So something new happened here. Okay. So instead of using the force way, the hard way, like finding the integral with parametrization and all that, that's exam number 3. That's hard. This is gonna make your life easier. Okay. So I'm gonna kind of jump to the Green's theorem. Okay, hold on. Let me keep you here. Okay, sorry. So I will show you in a second the other notes. There is kind of a proof for this. This is the Green theorem. Okay. So it's saying that if the curve is closed, well, in this case, well, let's say this is just for the example, the rectangle, right? If the example is the rectangle, and what I draw. So the integral over the curve of the vector field, okay. Sorry, the integral of the vector field over the curve, right? It could be found in another way. So remember what I said in Green's theorem, and these last theorems we're gonna do. The learning thing, the main important interpretation of this is that to figure out what is happening in the inside, you just need to check what is happening in the border around it. So you can think in practice, like imagine if it's not exactly that, because it has to be it's for vector fields, no? But if you want to happen what is in the middle, you just have to measure around. Sometimes, let's say, it's impossible to measure what is happening inside, but if you can measure the boundary, you can measure what is happening inside. Okay. So it's saying the integral on the boundary is equals to the integral over the region, over the whole thing, because this is an area integral of the derivative of q with respect to x minus the derivative of p with respect to y. So it's amazing. I think this is quite amazing, okay? So it's not like that, but imagine like if you are in a pool and you want to measure how much water is moving in the pool, or let's say how hot the water is over here, you just need to measure the boundary, okay? But you know, water is easy because probably the how hot it is here is gonna be how hot it's in everywhere, but it's not the same for here. So inside things are gonna change. So that's kind of what I'm trying to say. So this is the green theorem. This is another way, probably a third way to find this integral. You see how important this integral is, right? We have like 3 different methods now to find it. Okay, now, as I said, this also, remember, this is the work interpretation of this. So let's do it. So let's do this integral. So let's go jump right away to use the green theorem. So you guys encouraged to apply it. And it's easy. So I think now we have been suffering so much with hard integration that these last section are gonna be easy because we're gonna do the hard integrals in an easy way. So if you look at that, if you look at this integral of y squared dx plus s squared dy over the curve, and this is a close, it has to be closed, otherwise you cannot use this green theorem. Then with that like that, you can say what is p of xy and qxy. You tell me what is qxy, what is p of xy. Okay, you want 30 seconds to do that. So p is y squared, q is x squared. So this is p, this is q. So always for notation, p goes with dx, q goes with dy. Don't change the order, otherwise you're gonna try to hard to memorize otherwise the green function theorem or the Green's theorem formula. Okay, so like that. So by Green's theorem, this integral equals the double integral over the region of the derivative of q with respect to x. So let's do it here. So let's put it here. Derivative with respect to x of q. What is q? X squared. Minus derivative with respect to y of p, right? And this p is y squared. And then this is you can do dy dx or dx dy. So I'm gonna do dy dx. Okay, this is example number 2, I think. Well, that was example number 3. Maybe example number 3, yeah. So now this is 2x and this is minus 2y dy dx. But we need the region. The region is where C is the counterclockwise curve around the rectangle with vectors 0, 0, 2, 0, 2, 3, 0, 3. Okay, so it's from 0, 0 to 2, 0. And then from 2 to 3. And then from 0 to 3. Okay, so that's my curve. So this is easy because then y is moving y is moving between 0 and 3. And x is moving between 0 and 2. So we get integral between 0 and 2. And we have to find the integral antiderivative of with respect to y. So that will be 2xy minus 2y squared divided by 2, right? Evaluated between 0 and 3, dx. So when you evaluate that integral 0 to 2, you evaluate y, and between 0 and 3, you get 2x3 minus 2, 9. Oh, this is half, so this is just 9 minus 9. And then subtract the 0. So when you plug in the y at 0, you get 0, so that's fine. Look at how easy this is. Okay, this is like nothing like we had done. We haven't had to do parametrization of all that. So I'll explain in a second how you had to do it the hard way. Okay, so this is 6x. And now you go 6x squared divided by 2 minus 9x between 0 and 2. So that's 3. And then there'll be 2 times 2 is 4 times 3 is 12 minus 18. And this minus 6. Okay. So that's my final answer. Look at this. If I want to do this integral the other way, I will have to parameterize the curve. So how do I parameterize the curve? So this point, this one will be, this line is 3x. This line is 2y. This line is x0. And this line is 0y. So you'll have to do that, go curve by curve, and then find this one. Not that difficult. We could do it. We could do it. So we could do, just plug it in and probably divide 1, 2, 3, 4 curves. And then you can find it like that. So it's no big deal, but I think this is much easier. It's more fancy too. Okay. So a simple curve, a curve that does not intersect itself. So this is simple. That it now means that the personality of the curve. So the curve is simple. This is simple. And this is not simple. It's because this one is intersecting itself. So not simple. Closed curve, we already said that closed curve is one that wherever it starts, finish. This is not close. This is close. This is not close. So this is, behind of this, there is some theory of mathematical theory. Okay. So this is a simple closed curve. A closed curve that does not intersect itself other than having the same initial and final point. So a simple closed curve. This is a simple closed curve. But this is not a simple closed curve. It's closed, but it's not simple because it's intersected itself. And positive origin of a simple curve is counterclockwise. So how the wash moves, the wash moves counterclockwise, moves this direction. So if you're moving this direction, it's positive orientation. So if you are walking around here, this direction, the inside of the curve is gonna be on your right. You're moving this direction, so the inside is inside. Okay. Okay. Let's see. So now we have the general Green's theorem. It's the same thing, but not only for rectangles. So this, you have a vector field, but this is flat, no? This is not 3D. 3D is gonna be the divergence theorem, the next theorem that we're gonna see. This is flat. Okay, everything is flat. It's not, these arrows are not going out of the drawing. They're flat. So everything is flat here. Okay. So f of xy equals pxy qxy is a vector field in R2, and C is a positively oriented simple curve. This is very important. It has to be a positively oriented simple closed curve. So with interior region D. So we said it has to be, oh, counterclockwise. Oh, okay. So you see this one is counterclockwise. I think I said it wrong, right? So it has to move in the opposite direction of the clockwise, okay? So oh my goodness, I was saying, so I think everything backwards. So, well, if it's counterclockwise, if you walk in the direction of the counterclockwise, it's on the right. If you're moving counterclockwise, it's gonna be on the left. Okay, so the theorem, the green theorem, is in the positive orientation if it moves counterclockwise. Okay, so it has to move in this direction. So I was clarifying the what is counterclockwise, but really what we want to move in this direction. Sorry, when I just don't read the slides, it's easy to make mistakes, you see, but you learn better. This is the positive orientation, okay? So I can read the slides and just not make mistakes, but go super fast. But you know, it's not, there's more learning this way. Okay, so if the first partial derivatives of P and Q exist and are continuous at each point on and inside the curve C, then this is the Green's theorem, okay? But again, the curve has to be like this, curve, and it has to be this direction, and it has to be simple closed curve, okay? With positive orientation. Okay, so I think we can do one more and then we're done. So let's, for Green's theorem. So not this one, let's do the next one. Use Green's theorem to calculate circulation around the circle of radius 1 centered at the origin, oriented counterclockwise by the vector field. Okay. So we have a circle. So it has to be oriented counterclockwise. So it's gonna have this direction. And this is the vector field. Okay. So this is my P of xy and my qxy. So you guys tell me, what is P of xy? S squared minus y squared. And qxy, x squared plus y squared. Okay. So I need to find the integral over the curve, the line integral of pxy dx plus qxy dy. So you replace it, and this is the integral over s squared minus y squared dx plus s squared plus y squared dy. So then we place the Green theorem. By Green theorem, feel proud to say it. By the Green's theorem. So this is the double integral over the region. In this case, the disk or the region. Over the region of the derivative with respect to x of q, right? It's the opposite. Minus the derivative with respect to y of p. You see, this is super easy now, right? So it's basically you can't forget about parameterization. So this is the integral region, and the derivative with respect to x here is 2x, and the other is minus, so it will be plus 2y, right? dA is just dxy, right? That's dA. Okay, now that's the integral we need to find. But since we're on the circle, we have to parameterize this curve. Okay, we always parameterize this curve on the circle. So I thought we were almost done. We are takes time to do all these integrals. Okay, so let's do it here. So I had to parameterize, right? So radius is between 0 and 1 because it's the unit, which they said tell us the radius 1. And then theta is between 0 and 2 pi. Okay. So now we find and we replace. So because we are using parameterization, this is x r cosine theta, y r sine theta. We can use polar coordinates, but r is 1. So this is just x and y. Okay, so I replace it. I replace it here, let's say. So I have double integral 2 times cosine theta plus 2 sine theta. Oh no, but oh sorry. I'm doing the change of coordinates, right? So I don't need to. I need the r. Sorry, I need the r. I need my r. 2r, 2 sine, yeah. But because I'm doing the integral over the whole region. I'm not just doing the integral over the boundary. Okay, that's the difference. So please, careful this mistake that I just did. So when I finding the green function is over the curve, but turns out that it's better to find, or at least easier numerically, or by calculation, finding this integral inside the region. Okay. Well, no, I'm not sure it's easier, but this is the way we're doing it right now. So we have 2 times x, that's r cosine theta, plus 2 r sine theta. But when we find this integral, we learn that we need to multiply times r, and this is dr d theta. And now r is moving between 0 and 1, and the theta is moving between 0 and 2 pi. Okay. Okay. So now we multiply. So we multiply this, we get r squared. Ouch. R squared cosine and r squared sine. So we're gonna find first the integral with respect to r. So this integral between 0 and 2 pi, and the we can, yeah, so with respect to r is this 2r cubed divided by 3 cosine theta plus 2r cubed divided by 3 sine theta d theta between 0 and 1, right? So when I evaluate that, so I get, sorry, I don't have too much space here. So I'm gonna do integral between 0 and 2 pi, and then I go 2/3 cosine theta plus 2/3 sine theta d theta. Oh, that's looking better now, because when I subtract the 0 is 0, right? So that's that 2/3 cosine theta plus sine theta. And now I just need to find the last integral. So I'm gonna erase this. So I get 2/3. The antiderivative of cosine theta is minus sine theta, plus 2/3 antiderivative of sine theta is minus cosine theta, between 0 and 2 pi. Let's see, 2/3 minus 2/3 sine theta. Oh, no, plus. Antiderivative of sine, oh, no, minus. Sorry, I think one of those is wrong. Sorry, let me check. Antiderivative of sine, derivative of cosine is minus sine, yeah, minus. And this is just plus, right? Plus. So I get 2/3 sine of 2 pi is sine of 2 pi minus 2/3 cosine of 2 pi minus, and now evaluate that 0, 2/3 sine of 0 minus 2/3 cosine of 0. And then this sine of 2 pi is 0, and cosine of 2 pi, so cosine gets here is 1. So it's minus 2/3, sine of 0 is 0, and then plus 2/3, we got 0. So it must be correct. If we got 0, it must be correct. Okay, guys, so this is the end of Green's theorem. So next we are gonna do the divergence.